Today we will discuss about methods of proof. Methods of proof. Now, suppose P is a statement and Q is a statement. And we want to prove that P implies Q. That means P implies Q. It means if P, then Q. Suppose we want to prove this. There are various methods of proving such things. One is direct proof method. Other is proof by contradiction. The third one is proof by contrapositive. So we will be discussing each case one by one, and let's take an example. Now, suppose we want to prove this thing. If y is odd, then 3y plus y is even. Suppose we want to prove this. So it's an if-then statement. So therefore, what is happening is this. If y is odd, so y is odd, let this be P. 3y plus 5 is even, let this be Q. So we actually have to prove that P implies Q. The first is direct proof. So what do we do in direct proof? We assume that P is true and prove that Q is true. Okay. So let us see how this works using this example. So here, given that, now if we assume that P is true, it means Y is odd. So what does it mean? It means that Y is equal to 2m plus 1, where m is an integer. Any odd number can be written like this. So this implies that 3y is equal to 3, 2m plus 1, which is equal to 6m plus 3. This implies that 3y plus 5 is equal to 6m plus 3 plus 5, which is 6m plus 8, which is 2 times 3m plus 4. So this is nothing but twice of some integer. This belongs to an integer, 3m plus 4, because m is an integer. So 3m plus 4 is an integer. So this implies that 3y plus 5 is even. So this is known as direct proof, where we assume that P is true and prove that Q is true. Now, let us look at the second one. Proof by contradiction. So basically, we have to prove that P implies Q. So what we do in this, we assume that P is true, but Q is false. Okay. So what does it mean? Now, in this case, what is it is going to mean? It means that this implies that Y is an odd number, but 3y plus 5 is odd. Okay. Because what was your Q? Your Q is that 3y plus 5 is even. So we are doing contradiction. That means we are going to assume the opposite. Y is an odd number, but 3y plus 5 is odd. Okay. Now, as 3y plus 5 is odd. Now, this is an odd number. Okay. And 5 is odd. Okay. So 5 is an odd number. Now, if 3y is even, then 5 plus 3y will be odd. If 3y is odd, then 3y plus 5 will be even. So as 3y plus 5 is odd and 5 is odd, this would imply that 3y is even. Because if 3y is even, then only 3y plus 5 will be odd. This implies that y has to be even. Why? Because 3 is odd. So 3 is an odd number. 3y will be even if and only y is even. So this is a contradiction. This is a contradiction because y is odd. Hence, our assumption is wrong. Thus, 3y plus 5 has to be even. So this is known as proof by contradiction. Now the third is proof by contrapositives. Now, what do you mean by contrapositive? So for example, P implies Q. That means if P, then Q. So what is the contrapositive of this statement? Not P, not Q implies not P. Okay. So if we are not able to prove this, it is better that we prove this. This is known as proof by contrapositive. Now what was P? P was y is odd. And what is Q? 3y plus 5 is even. So let's again check this. Yes. So what will be not P? Not Q. Not Q is 3y plus 5 is odd. And what do you mean by not P? Not P is y is even. So let us try to prove that not Q implies not P. So let not Q holds. This implies that 3y plus 5 is odd. This implies that 3y plus 5 is 2m plus 1, where m is an integer. This implies that 3y is equal to 2m plus 1 minus 5. So this implies that 3y equals to 2m minus 4. So which is actually a multiple of 2 because m minus 2 will be an integer. So this implies that 3y is even, and this implies that y is even because 3 is odd. So this is known as proof by contrapositive. So rather than proving that P implies Q, it is always better to prove that not Q implies not P. Okay. Now there are two more methods of proof, general methods of proving. One is proof by exhaustion. Now, as exhaustion suggests grammatically, it means taking all cases into consideration. Okay. For example, prove that n is less than or equal to n square, where n belongs to the set of integers. So how do you prove it by exhaustion? We take cases. So case 1. So what are integers? 0, 1, 3, and so on. Minus 1, minus 2, minus 3, and so on. So case 1, if n is less than 0. So basically negative integer. Now if n is less than 0, n square is always greater than or equal to 0. Whether n is negative, positive, or whatever. So if n is negative, n square is greater than or equal to 0. This automatically implies that n is less than or equal to 0. Okay. In fact, n is strictly less than n square over here. Okay. So true. So that means case 1 takes care of all the negative integers. Then what is case 2? Case 2 is n equals to 0. So all the negative integers are taken care of. If you take n equals to 0, 0 less than or equal to 0 square. True. So I have taken care of 0 also. Case 3, n is positive. So for any positive natural number, it is always less than or equal to its square because n is a natural number now. So 1 is less than or equal to 1 square, 2 is less than or equal to 2 square, 3 is less than or equal to 3 square, and so on. So this is taking care of all the cases now. This is known as proof by exhaustion because we have taken care of each and every integer over here. Okay. Now, then we have something known as proof by induction. Okay. So what is proof by induction? Proof by induction generally works when we have to prove a general statement related to the set of natural numbers. For example, if we have to prove that 1 plus 2 plus 3 plus till n equals to n into n plus 1 by 2. Now we can see that there are infinite natural numbers. So how do we prove that? We cannot keep on choosing n because this is like sum of first n natural numbers. So you cannot keep on choosing n and doing the proof every time proving that LHS is equal to RHS. This is not going to help us because then we have so many natural numbers. So what do you mean by proof by induction? So what we do in this case, we do induction step. In induction step, we prove that the statement, suppose the statement is A is true for n equals to 1. So if we have 1, so LHS is 1, RHS is 1 into 1 plus 1 by 2, which is 1. So it is true. After we pass the inductions, sorry, this is basic step. After we pass the basic step, we have induction step. So in the induction step, we have to assume that A is true for n equals to k. Now note that to carry with the induction step, we should have the basic step in place. If the basic step is not holding, this proof by induction will not work. Proof by induction only works when we are sure that it is holding true for n equals to 1 or a natural number which is the least value. For example, if you want to prove a statement for n greater than or equal to 2, then we should check the basic step for n equals to 2. Okay. So now we come to induction step. Here we assume that A is true for n equals to k. So we are going to get one statement like this. Okay. Suppose this is B. And now we show that A is true for n equals to k plus 1. So to show, what do we have to show? 1 plus 2 plus till k plus 1 is equal to k plus 1 into k plus 2 by 2. This is we have to show. Now, what is the beauty of this thing? The beauty of this thing is this, that we know that what is happening till this term. This term is equal to k into k plus 1 by 2. And then we are adding k plus 1. Then you take k plus 1 common. So you get k plus 2 plus 1. So you will get k plus 1, k plus 2 divided by 2, which is RH. So then what is happening? We know that something is true for n equals to 1. Okay. And now we have proved that if something is happening for n equals to k, it automatically happens for n equals to k plus 1. Now what does this mean? We have proved that it is true for n equals to 1. Then by this step, it is evident that it is true for n equals to 2. Then again, it is evident that it is true for n equals to 3 and so on. So this is by principle of mathematical induction, we have proved this particular statement. This is known as proof by induction. So basically, we actually do not know, how to prove it for each and every natural numbers, because this is very, very huge. There are so many natural numbers in place. So what we do, we choose the basic step, we choose a particular natural number. So basically, it is like climbing stairs. So we verify that on step number 1, something is happening. And then we say, if at the kth step something is happening and we are able to prove that it happens at the k plus 1th step also, then we are going to use the basic step. That means it was true for step number 1, so it automatically is true for step number 2. Then it is automatically true for step number 3 and so on. This is known as proof by induction. There's one more method that is known as constructive proof. Now, constructive proof means you have to come up with examples. For example, if somebody says, show that x square plus y square equals to 50 has a solution in the set of integers. Suppose. Okay. So just come up with one example for which this is true. For example, 1 square plus 7 square is 50. So x equals to 1, y equals to 7. Similarly, minus 1 square plus 7 square equals to 50. So in fact, there are so many solutions, but if they say that show that it has a solution in the set of integers, even if you give one set or one pair of x and y, we're done, because we have to show that it has a solution in the set of integers. Or if they show that, if they say show that, this has a solution when x is negative, y is negative, then also we have a solution. So this is known as proof by construction or constructive proof, okay, where we generate examples to support our statement. So what are the methods of proof? So methods of proof are direct proof, proof by contradiction, and proof by contrapositives. So this is generally done to prove that P implies Q. Okay. If, then, something like that. Then we have proof by exhaustion. Okay. Where we have a lot of cases and we discuss each and every case. Then we have proof by induction. So where we have to prove a certain statement related to a very big set of natural numbers, basically. And then we have proof by construction. So this is all about proofs. Thank you.